Okay, I think we can start. Good evening, everyone. Today we have a first distinguished lecture after the pandemic era. And today we have as our speaker Peter Brändén. Sorry if I did it wrong. So Peter is a professor in the Department of Mathematics at KTH, Royal Institute of Technology. And Peter is also a Wallenberg Academy Fellow. Peter's primary research interests are algebraic combinatorics and positivity questions in various areas of mathematics. He received the Wallenberg Prize in Mathematics in 2008 and Göran Gustafsson Prize in Mathematics in 2019. And his recent work on Lorentzian polynomials proved a long-standing conjecture from 1970s, so-called Mason's conjecture, and today we will have an honor to learn more about Lorentzian polynomials. Thank you.
Thank you very much. And it's a true honor for me to be here. Many mathematical heroes of mine have been here or are here. So I'll speak about rather recent work with, see if this works. No. Maybe I use this. Yeah. With Jun Ha and Jonathan Leake, who's here. And well, so to start to motivate the questions I will be talking about, I've realized more and more that what I work on is negative dependence. And negative dependence traditionally models repelling particles in statistical physics, or maybe repelling random variables. So what is the setup? Well, the traditional setup is that we have some finite set E of sites, and they can be occupied by some particle or vacant, but just by one particle. So we have, then we can define a random variable, just a binary variable, 0 if I is vacant and 1 if I is occupied. No, it doesn't work. So if the particles were repelling, then I would expect different sites to be negatively correlated. So what does that mean? So we have some probability measure on the configurations, and the probability that we see I and J, sites A, I, and J being occupied should be less than or equal to what it would be if these events were independent. We have some repelling going on, so it should be less than or equal to what it would be if they were independent. And if they were independent, we would have products here. So this is the sort of simplest version of a negative dependence inequality. But there are others, so I won't list them all, but another one which is important for our purposes is log concavity. And log concavity of this sequence that tells you that exactly k sites are occupied. So this is also some kind of negative dependence inequality. And there is a stronger one, usually goes by the name of Newton's inequalities or ultra-log concavity. And this is the same thing, but we've normalized by binomial numbers instead. And this is stronger because the binomial numbers are known to be log concave. Right? So this is a bit stronger inequality. So, in particular, when it comes to independence in, for example, combinatorics or matroid theory or linear algebra, many of these problems exhibit strong negative dependence properties. And indeed, there are many conjectures formulated in matroid theory in the 60s and 70s that are very recently been solved. So I should start with a very simple problem. So we're given a finite set of vectors in some finite dimensional vector space. And we want to count the number of linearly independent subsets of size k. So if I've done this right, we have 5 vectors here, A, B, C, D, E. So F1 should be 5. And F0, we just have one empty set, so that should be 1. And then the number of 3 tuples of vectors here that are linearly independent, well, we choose, I guess, 5 choose 2 minus 1, which is 9, and so forth. So the problem is what can be said about this sequence, F0, F1, F2, F3, and so forth. So it's not hard to imagine that there is some kind of negative dependence going on here, because we're looking at independent sets of vectors. So given one vector, then there's a higher probability that this is going to cause some dependence. Okay. So we saw the Newton inequalities before, so they come from, well, what Newton observed about the coefficients of real-rooted polynomials. So if we have a univariate polynomial with only real zeros, then they satisfy this Newton's inequalities. So as we saw, this is one of these negative dependence properties, and one can argue that real zeros are indeed repelling in some way. So, because if they get close to, if 2 real zeros of a real-rooted polynomial coincide, then the probability of going off to the complex, to the non-real numbers is higher. So in some sense, they repel each other. So then this Mason conjecture that the Newton's inequalities should hold for these, the number of independent sets of each size. And the other classical problem is the problem of graph colorings. So we're in Waterloo, so maybe I don't need to say too much about it, but you know what a proper coloring is. It's just a coloring with the integers 1 to k, so that no edge is monochromatic. And again, one can imagine that there is some negative dependence going on, since neighbors are not allowed to be in the same state, so to speak. Right? So there is a statistical physics model for this too, and it has observed to be, or conjectured to be, negative dependent. And of course, there is the chromatic polynomial that counts the number of proper colorings. So for this simple example, this polynomial is real-rooted, but it's not in general real-rooted, of course. But it was conjectured to have some negative dependence properties. So if we expanded this chromatic polynomial in the standard basis, the coefficients here are called the Whitney numbers of the first kind. And this polynomial alternates in sign, so these unsigned numbers are these Whitney numbers of the first kind. And they were conjectured in different versions to be log concave. So I guess they were first conjectured to be unimodal, and just for the chromatic polynomial, but then they were extended in several different directions to matroids and to log concavity. So this conjecture actually applies then to the characteristic polynomial of any geometric lattice, so to any matroid. Yeah. So, and it was just in its most general form, this was proved then recently by Adeparasito and Katz. But in its in the form that I write it here, it was proved by Jun Ha in, I guess, 10 years ago, about maybe 13 years ago. But we shall see today a different kind of proof of it. So there are, well, so for a long time there was a lack of understanding of this negative dependence, and there was no real theory that could be applied to many of these problems. But in recent years, two different approaches have been developed. So the first one is to use the geometry of zeros of multivariate polynomials to say something about independence and negative dependence. And it was started to be, and this approach, I guess, started about 20 years ago. There was a paper by Choi, Oxley, Sokol, and Wagner about the connection between matroid theory and multivariate so-called stable polynomials. And at the same time, Gurwitz gave a wonderful proof of the van der Waerden conjecture for permanence using these stable polynomials. And then, and then Wagner further developed his approach and maybe going away a bit from zero restrictions. And then finally, Borchia, myself, and Liggett were able to come up with a theory of negative dependence using these multivariate polynomials. And since then, several conjectures have been proved using this partly. So maybe the most infamous one was the Caddison-Singer problem that was proved in 2013, I guess, by Marcus Srivastava and Spielmann. Okay. See if I can use this now. Now it works. And the other successful approach uses methods from algebraic geometry, namely Hodge theory. So then we want to deduce negative dependence properties from Hodge theory, and I guess the first application of this was due to Stanley, who proved the G conjecture for simplicial polytopes, or one direction of it. And he used this, well, I guess, so Hodge theory, there are several different inequalities in this Hodge theory, and he used the Lefschetz property to prove this G conjecture. And then there is what I told you before, the Heron-Rotter-Welch conjecture by Adeparasito and Katz, and also the positivity of Kastan-Lustig polynomials, which was a big conjecture in algebraic combinatorics for quite a while, used this too. And I guess, but the original, so Hodge theory was in some sense developed to prove the standard conjectures by Grothendieck, but this has not been done yet. Okay. So in 2018, June and I were lecturers at a summer school in Norway, exactly at this place. And he gave a talk about the Hodge theoretic methods, and I gave a talk about, well, gave lectures about these geometry of zeros methods to prove negative dependence properties. And we realized that there were so many common features in these, so there should be a sort of, one should be able to join these into one coherent theory. And this is how this theory of Lorentzian polynomials came about. So to motivate this, we will just mention a few elements of Hodge theory, namely the Hodge-Riemann relations in Hodge theory and what they are. So for this, we yeah, for the purpose of this talk, we might simplify it to have the setting of a graded R algebra. So we just quote by some homogeneous ideal, so we have a graded ring over R. And we assume that the top piece, AD, is one-dimensional. So since it's one-dimensional, we can fix some linear isomorphism between this top piece and R. And the other gadget that we need is inside the first piece, we should have some open and convex cone, which sometimes is usually called the ample cone. So we have a graded R algebra, we have some way of getting real numbers from it, from the top piece, and we have an open convex cone. So given that, one can state the Hodge-Riemann relations at certain quite complex inequalities which state that certain bilinear forms are positive definite. But I don't expect you to grasp this, but just the first two Hodge-Riemann relations. So these Hodge-Riemann relations, there's one for each integer between 0 and d halves. So let's understand the first two of them. So if k is equal to 0, well, then this just says that this product is positive. So that's not hard to understand. So the first, or the 0th Hodge-Riemann relation just says that when you multiply these elements in the cone and take the degree, we get something positive. And if we massage the first Hodge-Riemann relation, it also says something that looks like some negative dependence property. And what it says is that, well, these numbers here, they satisfy the Alexandrov-Fenkel inequalities. And and these are usually satisfied for the mixed volumes of convex bodies. But we see that this is some kind of log concavity, and indeed, if we just have two different linear forms, L1 and L2, then this amounts to just log concavity. And this is what can then be used to prove these log concavity statements in matroid theory. And this is what June did. But you then have to you then have to sort of know the algebraic geometry and the combinatorics of these algebras that you have. Okay. So the classical examples are, I guess, the classical example is Kähler manifolds and projective varieties. And then Stanley observed that you can use these projective varieties to get these inequalities for polytopes. So polytopes is also an example. And McMullen gave a combinatorial proof of this. And then Elias and Williams proved it for these Serger bimodals to get the positivity of the Kasten-Lustig polynomials. And then finally, Adiprosita, He, and Katz, they designed this sort of, it's not, this is just, well, a combinatorial definition of these Chow rings of matroids, and you cannot directly use projective varieties to prove it, but they could sort of more or less take the philosophy of McMullen to prove from scratch that these Chow rings of matroids satisfy the sort of, they could develop a Hodge theory for Chow rings of matroids by intricate inductions. Okay. So how do we sort of merge these two theories? So is there a common sort of polynomial approach to these two approaches? The first approach was the geometry of zeros of polynomials. So maybe we want to relax this property that we're talking about zeros of polynomials, but also we want to get away from maybe from the algebras and the setting of Hodge theory. So first we need a polynomial. And that we get from, this is sort of classical how you define this volume polynomial given the setup from Hodge theory. So what we do, we had this degree map from the top piece to R. So if we take a sort of a generic linear form, so we have variables ti, and these xi's were the generators of the algebra, and we raise it to the power d, we get something in the top piece. So we take the degree of that. And this is going to be a multivariate polynomial. So we can get polynomials out of this algebraic setup. And how do these, and we saw that in this Hodge-Riemann relations, we had these degrees of multiplications of different linear forms. So how do they translate into the polynomial world? Well, so if we have some vector in Rn, we can, of course, form the corresponding linear form in the first piece here. And if we take the directional derivative, meaning just, I guess, yeah, I've written it there. Yeah. Meaning just the sum ai di applied to the volume polynomial. Well, since this degree map is a linear map, this jumps into the argument here and amounts to just multiplying by L. And if we iterate this, we see that if we take several directional derivatives, this amounts to just taking the degree of a multiplication of L different linear forms. And these were exactly what appeared in this in these two statements. So the first one was that this was positive, and the second one was that it satisfies the Alexander-Frenkel inequalities. So this then leads us to the definition of what is a Lorentzian polynomial on a cone. So we have a homogeneous polynomial of degree d, and we have some convex, open and convex cone in Rn. And then we call it K Lorentzian if these two properties hold. So if we have positivity of these mixed directional derivatives, and if the Alexander-Frenkel inequalities hold. So this may look as may seem to be a very naive definition, just mimic the two first the two first Hodge-Riemann relations and think that we should have a working theory. But anyhow, we get a lot of good examples, important examples from Hodge theory. So if we can have a working theory around them, then it would be something nice. And we also have other examples that are classical. The determinant is Lorentzian because these inequalities are known to hold. These are just a mixed determinant, and these are known to satisfy these properties. But if you know what a hyperbolic polynomial is, and I know there are at least 2, maybe 3 persons, maybe more, in the audience that know what they are, and these are just by design also hyperbolic these are Lorentzian on its hyperbolicity cone. So we get we have a large set of examples of these Lorentzian polynomials. So these Lorentzian polynomials on cones were first studied by June and I, but then we studied it when the cone is just the positive orthant. So when the cone is the positive orthant, we call them just Lorentzian. So now we will see how we want to arrive at a characterization of Lorentzian polynomials that sort of, and from that we will see how matroid theory comes out of these Lorentzian polynomials. But first, some examples. So these homogeneous stable polynomials are always Lorentzian. And stable polynomials are polynomials that are non-vanishing when all the variables are in the upper half plane. So for example, and these are very much related to hyperbolic polynomials. But it's when the cone is the positive orthant, then we call them stable polynomials. And another important set of examples comes from convex bodies, and it turns out that if you take the volume of a Minkowski sum of convex bodies, then Minkowski already known that this is a polynomial in the xi's, and it turns out that these are Lorentzian, from which these the original Alexander-Frenkel inequalities come from. But also many polynomials in algebraic combinatorics, Schur polynomials and Schubert polynomials, and there's a whole set of conjectures about important classes of polynomials in algebraic combinatorics that are then observed to be Lorentzian or conjectured to be Lorentzian. And also, as we shall see, various matroid polynomials are going to be Lorentzian. Okay, so now to the connection between Lorentzian polynomials and matroid theory. So there are many different names for this, what we call M-convex here. But it's just an extension of the definition of a matroid to set systems which are in Zn instead of 0, 1 to the n. So if you know the basis exchange axiom for matroids, you should be familiar with this. So it says that if you have two vectors alpha and beta in your set B, then it says that okay, and if alpha I is greater than beta I, so in this direction alpha is greater, then we should find some j's such that beta j is greater, so we should be able to say go up. And then we should subtract ei, so we should go here one step, and we should get another point which should be in B again. So this M convexity says that we can sort of find some discrete line between alpha and beta in some sense, or at least a connection between it. So in a discrete sense, this is what we mean by convex then, M convex. And M stands for matroids. But they're also called polymatroids or integer points of generalized permutahedra. And there are other names for them too. And indeed, if we restrict it to 0, 1 vectors, these are exactly the set of bases of a matroid. So the next thing we need to do is, so how can we get a set system out of a polynomial? Well, we look at this. We look at the support of the polynomial, namely the vectors alpha for which the corresponding coefficient is non-zero. So this is just then the set of exponents for which the corresponding coefficient is non-zero. So this way we get a set system out of a polynomial. So the first sort of indication for why these there's a connection between the geometry of polynomials and matroid theory is this theorem from 2004 by Choi, Oxley, Sokal, and Wagner that says exactly this, that if f is a stable and homogeneous polynomial with non-negative coefficients, well, we don't have to have non-negative coefficients, but I don't know what. But then the support of f is M-convex. So for any stable polynomial, homogeneous stable polynomial, we get an M-convex set. And it was a question of, can we go the other way? So given an M-convex set, can we find a polynomial for which it is the support of? But we can't. So one of the most famous matroids, the Fano matroid, or the Fano plane, is not the support of any stable polynomial. And one can prove that no projected geometry is the support of a stable polynomial. But there is a remedy for this, namely this. So there is a characterization of Lorentzian polynomials in terms of M-convex sets. And it goes as follows. So say now that we have a degree D homogeneous polynomial with non-negative coefficients. Then f is Lorentzian if and only if two conditions are satisfied. So the first is just a combinatorial definition saying that the support is indeed M-convex, which is then quite easy to check. And the other one says that we just have to check that certain quadratics have exactly one positive eigenvalue. And this is why it's called Lorentzian. So this Lorentzian refers to the Lorentzian signature, which is plus, minus, 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 minus. So it should have, so here we say at most one eigenvalue, but since the coefficients are non-negative, this means that it has exactly one eigenvalue if it's not identically zero. But anyhow, so what this says is that if we differentiate with respect to just the coordinate axis, so we just take usual partial derivatives, and we do it until we get a quadratic. So we do it d minus 2 times. Then we can look at the corresponding Hessian, and we check the eigenvalues of that, and if all of them have exactly one positive eigenvalue, or at most one positive eigenvalue, then they are Lorentzian. Then. And this is also a quite simple check. It's quite fast to check the signature of a matrix. So this then, yeah. So instead of having this definition with all these directional derivatives, we have reduced it to the checking a combinatorial condition and a linear algebra condition, which is quite useful. And we also have a converse. Given any M-convex set, we may produce a Lorentzian polynomial with that support. We just take the exponential generating polynomial of it. And this is also always Lorentzian. So it goes both ways. So in some sense, these set of Lorentzian polynomials, they characterize M-convex sets and matroids. So we have a sort of one-to-one, many-to-one in one direction, but anyhow, they characterize M-convex sets. So how am I doing in time? Is it 20 minutes or 15 or 20? Okay. So now we want to use this characterization to see how Mason's conjecture actually follows quite easily, given this theorem. And this was proved independently and at the same time by another set of authors too. So now we have this. So we're back to the Mason's conjecture. So but now we phrase it in the terms of matroids. So we let I be the collection of independent sets of a matroid. But if you don't know what a matroid is, you can think about this, that I is this collection of independent sets of vectors in a vector space. And then these Lorentzian polynomials, these are multivariate polynomials, so we form sort of the multivariate generating polynomial of that. And we have some extra variable here because we want to make it homogeneous. Because Lorentzian polynomials, these are homogeneous polynomials. So we have two conditions to check now. We have to check that the support is M-convex and that these when we differentiate d minus 2 times, that it's that it has the Lorentzian signature. So one thing we get for free, the support is of course M-convex since it comes from a matroid polynomial. So this is free. But then we want to differentiate with respect to the variables here. But if we differentiate to one of these variables, then we just get the contraction. So this is also for free if we want to do induction. So by induction, we just have to differentiate with respect to this dummy variable here, down to quadratic. And this is the polynomial you get. So we need to prove that the Hessian of this polynomial has at most one positive eigenvalue. But this is just a simple exercise in linear algebra. So this is how but of course we had to work a bit to get to the characterization of Lorentzian polynomials. So it's not, but the proof of Mason's conjecture given this characterization is quite simple. And then this Mason's conjecture follows from the defining the definition of Lorentzian polynomials that they satisfy these Alexander-Frenkel inequalities. So you're going to get, I won't do the derivation of that, but it's also, you can imagine that it follows directly from the Alexander-Frenkel inequalities. Okay. So now to the second part of the talk. So now we've mostly talked about Lorentzian polynomials with respect to the positive orthant, but there are several reasons why you want to look at other cones than the positive orthant. And one reason is you want to look at simplicial fans and their Chow rings. So what is a fan? Well, a fan is just a collection of polyhedral cones in some Euclidean space, which satisfies that every non-empty face of a cone in this fan is a cone again, so it's hereditary in some way, well, in this precise way. And also that the intersection of two cones is again a face of both, so it's in there in sigma again. And it's a simplicial cone if each cone is spanned by linearly independent vectors. So this is then a simplicial cone in R2, and this is in R3 where we've intersected it with the unit sphere, I guess. So these are simplicial fans. And how do we get a ring out of them? So what do we do? So we look at, so for each one-dimensional ray of this cone, we pick some vector, rho 1, rho 2, up to rho m. So these are the rays of the one-dimensional cones. And then we may form an ideal, which is the Stanley-Reisner ideal of this fan. And it's given by the monomials indexed by these rays, for which the corresponding rays do not generate a cone in sigma. It's called the Stanley-Reisner ideal. And then we have another ideal too, which are more about the positions of these rays. And these are then linear forms given by sort of hitting these rays with any functional. So for any functional here, we get a generator of this ideal. But it's enough to take finitely many. And then we quote by these two ideals. And we get the chowering of this simplicial fan. So now we have one of the, so this is of course a graded R algebra, so we may talk about these Hodge-Riemann relations and the and this volume polynomial of this of this ring. But we need some cone, and there is one canonically defined open convex cone, which is sometimes called the ample cone. But I won't define what it is because it's not that important for our purposes. But there is one. But there's a way of sort of projecting down this star by just, so this is, if you're familiar with simplicial complexes, this is the corresponding, this corresponds to taking the link with respect to a face. But here we have cones instead. So what we do, given one cone sigma, we can quote by the subspace generated by sigma, and then we get a set of cones now. Yeah, this is just the quoting out by this R sigma, and this is called the star of sigma. So then we call this simplicial fan hereditary Lorentzian because we want this Lorentzian property to hold for all of these stars. So we call it hereditary Lorentzian if two properties are satisfied. The first is just that we want to be able to define this degree map, so the top piece has to be one-dimensional. And the other one is just that we want these Hodge-Riemann relations of degrees 0 and 1 to hold. And these were these ones that we've seen before. So we want positivity, and we want Alexander-Frenkel inequalities. So if these two are satisfied, then we call it hereditary Lorentzian, this simplicial fan. And in recent years, these Alexander-Frenkel inequalities, and the Hodge-Riemann relations have been established for certain sets, so certain simplicial fans related to matroid theory and to convex polytopes and so forth. But now we have sort of a characterization for when such simplicial fans are indeed Lorentzian, hereditary Lorentzian. And this looks a lot like the theorem of June and I had for Lorentzian polynomials, and it essentially just reduces everything to degree 2 again. So the first one is that we should have positivity for these for any maximal cone, which is easy to check. And then we have that this corresponds to this M convexity, but now this condition is even simpler. It's just that it should be connected. We just have connectivity, which is not a strong requirement. But the third one is then where everything happens, is that if we take the stars so that we get a two-dimensional fan, then this should satisfy the Hodge-Riemann relations of degree 1. So, and equivalently, And our equivalent statement to L is that this volume polynomial has at most one. The Hessian of that, of the corresponding star, has exactly one positive eigenvalue. So this is then three properties that are easy to check, so we may apply it to our favorite fans. And what we apply it to is the Bergman fan of a matroid. So what is that? So we have a matroid without loops, and then this Bergman fan lives in R to the E, where we quotient out by the all ones vector. And the rays are just for each proper flat. So it's not empty and it's not the whole set. We just take the corresponding sum of the basis vectors. And then the cones are given by chains of flats. So we just take the sum of these, the convex hull of these, or conic hull of the corresponding rays in this chain. And when we then look at its chowering, and it has dimension r-1, since we can at most have r-1, where r is the rank. We can at most have r-1 proper flats in proper containment. So now we'll indicate how to prove that this is hereditary Lorentzian, and this is what Adeprasito and Katz proved in their paper to prove the Heron-Rotter-Welch conjecture. But it follows quite easily from this characterization again. So it's not hard to see that the dimension of the top piece is 1. And indeed, for any maximal chain of flats, one actually has that these two monomials agree. So then one can define the degree map to just send one of these monomials to 1. And the beautiful thing is that if we take a star for any sigma, then we get the chowering of a matroid for a smaller rank matroid. So this sets everything up for induction again. And it's easy to see that this is simplicial and connected. Connectivity, well, these are usually not hard to prove. So if we have this theorem again, so what we needed to prove the positivity, but this, well, the degree is 1, so always. So this is always hold. And we mentioned that this is always connected whenever it is two-dimensional. So this holds too. So the remaining property that we need to prove is that this volume polynomial of the star has at most one positive eigenvalue whenever this is two-dimensional. And this is also not hard to prove because, well, so what it amounts to is to prove that this volume polynomial has at most one positive eigenvalue when the rank is 3. And one can actually compute this explicitly where we sort of can see that it has at most. So we can write it as a square minus a sum of a bunch of square, and this exactly says that it has at most one positive eigenvalue. So this is a hyperbolic polynomial. So should I wrap up now? Or? Yeah. So I should just mention how, yeah, so the Heron-Rotter-Welch conjecture then follows from the Alexander-Fenkel inequalities again by just picking two vectors in the closure of this cone and look at the corresponding polynomial. So I guess I stop here.
Thank you for the great talk. So now we'll have Q&A part of the talk. So when you have a question, please raise your hand. We want to record the audio so that it remains on the recording. And yeah, so I will be there with the mic, and then you can ask the question. So who is the first one? Sorry.
Is this working? In the case that you're working with a symmetric polynomial, is there any connection between Lorentzian and positivity when expressed in other bases? Sure, obviously there's some going on there that you've mentioned.
That's an excellent question. Well, I thought for a while that if you had one of these stable polynomials, that it could be that they always were sure positive. But unfortunately, that failed. I thought one could use this to maybe attack there is this conjecture about the permanent on top conjecture, but that it didn't work out. But there are so you get a lot of inequalities for symmetric stable polynomials and Lorentzian polynomials too, that come from the Alexander-Frenkel inequalities.
Oh, sorry. Okay, I didn't want to put anyone on the spot.
So one of the things that's really nice about the theory of stable polynomials is that you have a very nice theorem about which linear maps preserve stable polynomials. Is there anything like that
Yes.
for Lorentzian polynomials?
For Lorentzian polynomials, there is. When the cone is the positive orthant, then June and I proved one direction of it, that if this, well, so the characterization of stability preservers is in terms of the symbol, right? So if you have a linear map on polynomials and the symbol is Lorentzian, then you can prove that it preserves the Lorentzian property. But we found that there are examples of linear operators whose symbol is not Lorentzian, but it preserves Lorentzian property anyhow. So the other direction is still sort of open. So it would be nice to have a characterization of both ways, but then you would have to extend the Lorentzian property.
Okay, do we have any more questions? Okay, so we save the question for the reception, I assume. Or someone wants to ask the question still to be recorded? Okay, if not, I wanted just to make an announcement that for those who want to learn more about Lorentzian polynomials, Jonathan is teaching a graduate class this term on Tuesdays and Thursdays. And then the second announcement is that we have reception. So please join us. Thank you again.
Thank you.